Today I'm going to talk about incorporation of thunderstorms and tornadoes into wind load codes and standards. And as kind of a general overview, I'm really going to talk about kind of what we've typically assumed in wind load codes and standards up to this point, and then kind of maybe some of the directions that we're starting to go. And thunderstorms and tornadoes play a huge role in kind of really the future of codes and standards, and I'll talk about that part, and I'll also talk about some of the research that is kind of leading into the wind load codes and standards. But first, really, I kind of want to start with a kind of a history of the practice of wind engineering from the very beginning. And, you know, early wind tunnel testing, which is really kind of the primary tool that we use today for data that gets into codes and standards, were done in aerospace tunnels. And in the 40s and 50s, it was realized really that those tunnels did not produce realistic loads when compared with full scale. So one of the first comparisons of a full-scale experiment with aerospace wind tunnel data was the Empire State Building in New York City. And they used, the researcher on that project used a barometer to measure pressure, and what he found was that the barometer was fluctuating all over the place. And so if we look at kind of an actual wind speed time history, what it actually looks like, and so you can imagine that that's fairly related to the loading as well, is that there are quite a bit of fluctuations in the data. So this is a 15-minute record of wind speed, and so you can imagine the fluctuations in loading would look similar to that. And so, in short, really, what we didn't do in the 40s and 50s, you know, aerospace tunnels are usually based on smooth airflow, you know, for aerospace applications that are well above the ground, and what we see that obviously if we're closer to the ground, we're going to have to deal with turbulence. And so the major thing that we weren't doing we really weren't replicating the actual wind properties and hence the loading properties. And so the wind properties, I'll kind of use a general term called the atmospheric boundary layer. And the atmospheric boundary layer is just simply where the friction from the Earth's surface influences the wind and really hence the loading characteristics. And so some of the assumptions that we make with that are kind of the following. Kind of the major assumption that we make is that statistical properties of the wind, whether it be wind speed or direction, are independent of some space and time scales. And so for spatial scales, we typically assume that's much larger than the building scales that we're interested in. And in time, typically we assume, at least in codes and standards, about a 1 hour time period. And this 1 hour time period is related to, if you look at the frequency content of the wind, generally there's not a lot of energy in these time scales. So basically it's a good separation point to separate out kind of these larger scale wind fluctuations that are over days and years to really more turbulence, which is occurs over scales of an hour or less. And so another thing that we assume with this kind of independence in space and time is that we can kind of describe some of these processes that go on with simple kind of Gaussian normal distribution processes to estimate peak loading. At least in the early days, we relied on that assumption. Other assumptions that we make, obviously, as most of us are probably structural engineers, we're interested in the properties of strong winds. And so with strong winds, there's other assumptions to be made. One is really that there's no temperature or buoyancy effects in the wind. And then a couple other things that are going to be important as I kind of get to talk about thunderstorms and tornadoes here at some point is that the wind flow is horizontal and that there's really no pressure gradient over the areas that we're interested in. And so let's get into kind of a little more specifics of this atmospheric boundary layer, what I talk about. So on the top left is the same wind speed trace I showed back in the beginning. And so typically in wind engineering, how we handle that is basically, again, so we assume basically the wind, a mean wind doesn't change over these hour-long time scales, for example. So from that, we're able to calculate a mean wind speed, which is shown by the red line here and U bar. And so if we subtract this mean wind speed out, what we're left with is basically all the fluctuations, which look exactly the same as the wind speed trace above, except now we have a kind of a zero mean process. And so what we can take from this atmospheric boundary layer are basically these profiles with height. And so, for example, I've kind of normalized these profiles to show them on the same graph. So here is a mean wind speed profile with height. So it's normalized by some reference velocity at some reference height, which is at 1. So the wind speed is normalized by the speed at some reference height. Really what I want you to see here is obviously the mean wind speed increases with height. So anybody that's dealt with wind or wind design takes that into account. So we have an increase in mean wind speed and height, and then here is a turbulence profile. So typically I have IU there, so that's turbulence intensity, and that's really kind of the standard deviation of the fluctuation shown here over the mean wind speed.